Yeah, so hi. So this is the second lecture on RAG, and earlier we had I showed you what is I told you a little bit about what is RAG and how it works and why is it even needed, and I talked a little bit about the topics already. Let me go on to topics again and show you. So these are the first part of the topics. So we'll be covering query embedding, and in this video I'll try to cover only the first part 1.1, and it contains dense models, sparse models, and hybrid embeddings. And these are the rest of the topics for the upcoming videos, just for you to know the topics and the flow. Okay, right. So now we have in embedding models, right? So we have what is known as dense embeddings, sparse embeddings, and hybrid embeddings. So what are embedding models in the first place, and why do we need them? So we have text in the form, we have all the data in form of text when we are dealing with a large language model. We convert the text, that is queries and documents, into vectors to numerical representation that capture the semantic meaning. So we cannot give directly text to a large language model, right? It is large language model is nothing but matrix operations at the base of it. So we need to convert them into numeric form. So why do we need embeddings? In order to enable the semantic search, or to match the queries with the document chunks, and to improve the retrieval accuracy. So this is why we need embedding models. And how many types of embedding models do we have? We have what is known as dense embeddings, sparse embeddings, and hybrid embeddings. So dense embeddings capture the semantic meaning. The sparse embeddings capture the keyword or the actual keywords. It's based on the actual keywords. And hybrid embedding is just a combination of both, and they're formed using techniques like score fusion and vector merging. So let's start with what are dense embeddings. Yes, so dense embeddings convert the text into high-dimensional continuous vectors. The dimension is usually say something like 256 to 4096 as well. So dimension stays in between, and they capture the semantic meaning. Okay, and the main dense embedding model that we would come across when you're working with RAG or any other system would be MiniLM, BERT, OpenAI, or there's also BGE. You'll come across this as well by Beijing AI group or someone. So these are the main, and how do they work at the end of it, right? When you have an input token or input text, say I love machine learning. So this is the whole sentence that we have, right? It is converted into subwords first. So we'll have what is known as a classification token, and then we'll have each of the tokens, right? Machine and learning, and we'll have a separator token. This is to separate between sentences, and they're converted into token IDs and positional embeddings. These are the special tokens that needs to be added as well, and they are passed into BERT model, and then they use self-attention. So each word here looks at every other word and builds a context-aware representation. So this is the first part of dense embeddings. So what we do in actual coding, we just give the model the input text, and it gives us a vector representation. But at the back of it, like in the black box, this is all happens. So we have the input token first, and then we convert it to subwords, and then we tokenize using BERT, and it uses self-attention. You can read the paper. Attention is all you need. There's a famous paper, you can read that, and how actually transformer works. And BERT is one way of transformer. It's bidirectional encoder representation of transformer. And so we have, suppose we have a word like bank. Bank is different in two sentences. If I say like I am going to deposit my money in the bank, and another sentence is like I'm going to the river bank for a chill time. So in both the cases, bank is different. So we use BERT in order to understand the actual meaning. It is different for different vectors. And the next would be contextual encoding. In contextual encoding, what we do, we pass each tokens into a BERT that we already told, and model looks at the context. So this is what I just spoken, right? And in the next step, we have three types of pooling. mean pooling, max pooling, and CLS pooling. So when we need only one vector per sentence, right? So we aggregate the token vectors that we already got for each token, and using these techniques, we'll get only one vector, right, and one fixed size. So that way, fixed size dense vector. And here, all of the part of dense embeddings will come to an end. So mostly this is it, and the sizes of the fixed final vector that we get is something like this. So for mini LM it's 384, for BERT base it's 788, and for OpenAI large it's going up to 4096 as well. And for the interview point of view, when you say that you have used an embedding model, you should remember its dimension as well. And the interviewers will ask. I faced this question in an interview. I said that I used text radars embedding model, and they asked me what dimension it is. I was able to recall at that point of time, but if you're not able to recall, they'll get a doubt, right, if you really used or not. So this is one thing you need to keep in interview point of view. I'm writing here just so that you will know interview importance. So you should know that. And the similarity, how is the similarity done? It is using cosine similarity that you all are already aware of, right? So we need to use cosine similarity to compare the vectors. So when we're using RAG, we need to compare the vectors in our external knowledge base or the vector database and retrieve the most similar vector to our query. And one more interview importance question is that one interviewer asked me, why do we all use cosine similarity and not sine similarity, right? So think of it and let me know in the comments if you're able to answer that. So it will date back to our 10th class trigonometry. It's as simple as that. This is a small clue you can work on. So this is mostly about the dense embedding. So the main thing that you need to remember about dense embedding is that they capture the semantic meaning, and we have no relation to the actual words and the final vector representation. So if you try to take the vector size of say 1024 and try to understand the sentence that you have at hand, you'll not be able to do it, right? So this is about it. So next let's go to now talking about VM25. So we already have a vectorizer or embedding technique in machine learning, right? So which is count vectorizer or TF-IDF vectorizer. So if we have something like I love deep learning and I love machine learning, these are the two sentences that we have. So for the first sentence, second sentence it will be all ones except machine learning. It will be a zero here because we don't have machine, because we don't have that word in the first sentence. For the second sentence, we'll not have we'll have a zero for deep because we don't have a word in that sentence. So this is just for a five vocabulary text. So what if we have a text containing a full documents? Let's say there are two annual reports, of one of financial year 2024 and one of financial year 2025. Then the corpus will be very huge, right? And we'll have a lot of zeros, more than any kind of numbers or integers. We'll have more zeros. So that's the reason why it's called sparse embedding, sparse technique, sparse matrix or sparse techniques. So in BM25, so where does the 25 come from? 25 doesn't have any kind of significance. It's just the version of the model that they released, and that model was famous. That's the reason that went on to stay like BM25, best matching 25. And this is mostly used in the search engines or the search techniques, right? It's a classic scoring function used in search engines to rank documents based on how well they match a particular query. So the ranking is a ranking algorithm that scores how well a document is to a query based on three things. First thing is term frequency, inverse document frequency, and document length normalization. What does term frequency tell here? It tells how often a query word appears in a document, and how rare is the word across corpus is told by inverse document frequency. And document length normalization tells you that the shorter documents get boosted. So if it gives a BM25 gives a higher score if the document contains exact keywords found in a query, and let's say those words appear multiple times and the words are rare in the whole corpus, then we'll have a higher BM25 score. Okay, and so going to the formula of it, here there are important components in this formula. First is inverse document frequency. Inverse document frequency sums over, inverse document frequency boosts the rare words and downweights the most common words. So in text we might have words or pronouns like is, the, are. So they're not contributing to the meaning of the whole document or what it tries to tell, right? So in that case we can ignore those. So those are common words, and the inverse document frequency takes care of that. And apart from that, we have this term frequency, right? If a word appears many times in a particular document, then it should score higher in the term frequency, right? So we can have term frequency say 1, 5 or 10. 1 is a big jump because term frequency is here, and if it is a 1, that's fine. If it is a 10, then it lowers the whole score as such, right? So that's the reason if it is a 10, then there's no effect as such. And apart from that, we have this important components, which is document length normalization. If it is a long document, then the denominator here becomes very large and the score will get penalized. If it is a shorter document, the denominator becomes small and the score will be higher. So this will prevent the long documents from always ranking higher just because they contain more words. And here we have two tuning parameters. One is K. K is somewhere between 1.2 to 2.0 always, and it controls the term frequency saturation. And we have another tuning parameter which is B, which is a length normalization. It controls the length normalization. If it is a 1, then we do the full normalization. If it is 0, then we don't do any kind of normalization. And if it is 0.75, we have a balance between both of them, right? So in summary, BM25 score increases when document contains any kind of query words. In that case, what happens? This will get larger. Okay, the term frequency term will get larger here. And if the query word is rare, then the IDF score becomes larger. And if the document is not too long, then the denominator will become short and the overall score will be higher, right? So this is about the best matching 25, and now we'll talk about splayed. Okay, splayed is nothing but sparse lexical annotation with dual encoders. So in the name itself, we have some clue as to what it does, what splayed does. So we have three things in splayed. One is lexical retrieval. After that, we have what does lexical retrieval mean here. So it takes care of exact keywords and rare tokens and IDs. Apart from that, we have semantic understanding, which is about related word matching. So if we have say words like doctor and treatment, so related words are pharmacist or diagnostic, physician. These are the related words. These are added to the final matrix that we get, final vector or matrix that we get. And sparse vectors, so that why do we have sparse vectors? So that that can be indexed in inverted indices like Elasticsearch. So let's deep dive into the steps of splayed. So firstly, it is a query or a document is fed into a transformer like BERT, and then we'll get the subword tokens here. So we'll get the classification token or the separation token, and we'll get the subwords in each token. It uses BERT tokenizer to convert it into subword token and the CLS and ACP markers, separator markers. And after that, what happens? So the model outputs a vector for each token or a subword. So in this step, that happens. So splayed passes the tokens through a pre-trained BERT encoder, and we'll get hidden states for each token. And after that, the vocabulary scoring happens, right? So splayed uses MLM head, the mask language model head, for getting the logics of the vocabulary, and they're computed like the MLM head already knows most of the things, right? It knows the morphology, it knows the lexical variation, it knows the subword relationship, and it knows the linguistic associations as well. So these are already there in BERT's MLM head. So from this we'll get a matrix of size, say tokens into vocabulary size. Okay, and the logics are calculated as such. After this, sparse vector creation happens. So it uses both relu as well as log functions in order to do this. The raw logics can be negative. They can be too large, or the raw logics that we get from here, right? They can be negative, too large, or too dense. They can be many non-zero values as well. So Slade applies this log of 1 plus relu of the vector in order to get a decent vector as such, sparse vector. So what does relu do here? Relu's contribution is removing negatives. So why? Because tokens must activate positively, and log compresses the big value and makes the weights more stable. It smoothens the scaling as such. So what the result will be a huge vector of size is equal to the vocabulary size, and it will be mostly zeros because we will have a sparse vector here. After that, we have a learned expansion. Because the model scores the entire vocabulary, it activates not only the original words but also the related words. So I told you, right, if we have an input like doctor and treatment, and the output vector may include words like physician, hospital, therapy, etc. So this is known as semantic expansion. Okay, and after this, what do we have? So the next step is indexing. So these sparse vectors are stored in an inverted index, same as the classical search engine that we have, and similar to methods like BM25 already. And coming to the retrieval part, the query is converted into a sparse vector in the same way, right? The matching is done by a dot product between sparse vectors. Why do we need dot product here? So because we need non-zero terms. I mean, we have non-zero terms already, right? And it is more efficient. Only non-zero terms are compared here. That's the reason why it is more efficient. And this is known as a sparse dot product. It uses the lexical token weights here. So it is similar to BM25, but with learned semantic expansion. We are getting that in this step, and we have a token level weighting as well. That's the reason. And the training objective is a contrastive loss training objective. Given a query, we'll get the relevant documents have higher similarity scores, and the irrelevant documents are having lower similarity score, and the loss pushes these scores as farther away from each other as possible, right? So why do we need contrastive? Because Slade is a retrieval model and not just a language model, right? So in summary, what we have a query first, and then we predict all the related keywords. We keep only the important ones, and we search like a smart keyword engine. Okay, this is mostly about Slade. I will try to create another video so to talk about Slade in more detail and in more depth. So till now we have covered these two things. We have covered what are dense embeddings. We talked about various steps involved. We talked about the sparse embedding, but in some cases we might need a hybrid of both of these, right? So the dense embeddings might miss on the exact matches, and the sparse embeddings might fail on paraphrases as such. So we use we need techniques to combine both of them, like score fusion or vector merging. So let's talk about that. So what does score fusion does? So it takes the score of dense embedding and sparse embedding and just adds them up, weighted sum. Okay, we are using weighted sum here. And how to decide the alpha and beta here, these parameters, because if you want a higher importance for the keywords than the semantic meaning, then we have the beta parameter more here. If you want the semantic meaning of more important than just the touch of keywords, then we go for higher alpha score here, right? So here dense score may be semantic score or a similarity score, and the sparse score may be BM25 or a Slade score here as such. And this is used in OpenAI hybrid search. And in one more method, we use a vector merging technique. So we just concatenate both the vectors, and this kind of technique is used in vector DBs like VV8, Pinecone, Wilbus, or Vespa, etc. So when do we need to use this? When we need max retrieval accuracy, when the text or the data contains numbers, rate terms, formulae, code, and when you need more robustness involved, right? So we talked about the first section here. This is mostly it for the video. I just wanted to keep it short. So we covered this aspect here, 1.1, which is when we have query embedding is the main topic here, and we talked about embedding models, dense embeddings, sparse embeddings, and hybrid embeddings. And these are some of the other topics that we will cover in the upcoming videos. It's a long journey, to be frank. So we need to talk about query embedding, we need to talk about vector database retrieval, we need to talk about context augmentation, LLM generation, and grounded and up to date. So these are the kind of sections I felt comfortable in learning RAG. So I'll try to go in a similar fashion. And this is it for the video. Let me know if there are any kind of corrections or improvements to be made. And sorry if you want me to cover any other techniques as such. Chalo, thank you. Have a nice day. Bye. Happy learning.